In this video, I'd like to share some tips on two-layer PCB designs and what to watch out for when you're constrained to only two copper layers on your PCB, that is the top and the bottom layer. Two-layer PCBs are still quite relevant, especially for cost in higher volume. They are simple in terms of their build process. We don't have any internal layers, so to speak, to debug. We have a higher manufacturing speed typically, and the ability of many manufacturers to actually produce these two-layer PCBs, of course, if they're designed to certain constraints. The PCB you're seeing right here is an RF dongle, which contains a CC2500 RF transceiver you're seeing on the right-hand side, which is effectively a 2.4 GHz transceiver, controllable via SPI or UART. We have some matching network and connecting to a PCB chip antenna. On the left-hand side, we have an FTDI USB to SPI converter. This is an FT4222 HQIC that interfaces with the CC2500, and on the other end goes to a USB Type-C connector, which then I can then plug in to my computer. This is a two-layer board, but it demonstrates that for something as simple as this, and for many other projects, you might not need to go to a four-layer board, especially if you're producing designs in high volumes and cost is a very critical factor. We have USB 2.0 high speed, we have SPI, we have RF, some CMOS oscillators, all on a fairly space-constrained small two-layer board. This board is approximately only 40mm by 15mm wide. So again, in this video, I'd like to share some tips of how I typically go about two-layer designs and when you might want to go with those. In future videos, we will be looking at this RF dongle on the left-hand side in combination with the PCB on the right-hand side, which is a micro quadcopter control PCB, which also contains a CC2500 transceiver, and we'll go through writing drivers for the CC2500, PCB chip antenna design for your PCBs, and more. And that's the reason why I also created this RF dongle on the left-hand side, so I can create a base station with my desktop computer that communicates with the micro quadcopter drone. But more on that in future videos. A huge thank you to PCBWay for sponsoring this video. I had these RF dongles manufactured and assembled by PCBWay in China using their PCB prototyping service. As we'll see in this video, this is a simple two-layer PCB, so we could use PCBWay's fast turnaround prototyping service at a very, very low cost. Although they do have many options for the prototyping service up to 14 layers, for the advanced service up to 60 layers, and many different customization options, including now also for silkscreen, they have UV printing, which I'd like to try for a future video as well. Make sure also to follow PCBWay on Instagram to see all the cool designs they're producing, as occasionally you might see some of my PCBs pop up there as well. A huge thank you also to Altium for sponsoring this video. I did use Altium Designer to design this RF dongle PCB, but the tips in this video will be applicable to any ECAD tool. If you would like to give Altium Designer a try for yourself, make sure to check out the link in the description box below, or go to altium.com/YT/PhilsLab, and you can get yourself an Altium Designer free trial, as well as 25% off your first license purchase. Along with your free trial of Altium Designer, make sure also to check out Altium 365, which contains many cool features such as library management, mechanical co-design, design reviews and markups, online viewers, and much more. Again, links will be in the description box below. Finally, to help you out with part searches and finding the right parts for your designs across many different distributors, make sure to check out octopart.com. I happen also to be creating a few videos for the Octopart YouTube channel, so make sure you're subscribed to them as well. The first point I'd like to drive home regarding two-layer PCB designs, and probably one you're well aware of, is their rather cheap cost. It's one of the least expensive types of PCBs to produce, at least in a standard configuration, assuming no particular requirements. If we go to PCBWay or your preferred PCB manufacturer, even in low quantities such as 10 PCBs, if we do 50 by 50mm, and just a standard two-layer FR4 PCB, we can get them for about 50 cents a piece, compared to, for example, a four-layer PCB, which will be 10 times the cost, at least in these low quantities. Again, keep in mind it is very dependent on what parameters you choose here, including track spacings, sizings, hole sizes, and much more, all of these parameters, but this is just as a demonstration. Other than cost, check out also the build time. So for example, this typical build time for a higher layer count PCB for 4 layers might be 4 to 5 days or above, whereas for 2 layers, because this is also a simpler process and typically more demand for 2 layers for these PCB prototyping services, they can get this done in 24 hours, if not less. Now, we just looked at low production quantity costs, but for example, if we say go for production quantities of 10,000, for 10,000 two-layer boards, we're looking at about 28 cents per board, whereas a 4-layer board, we're looking at about 38 cents per board. Now, although that might not seem much in quantity, for certain products this can definitely matter. So there are certain reasons for going with two-layer boards. Again, that is cost, that is manufacturing ease, speed, And simply, in many designs, 2 layers might be all that is required. So for example, this RF stick PCB, this RF dongle, because there's not particularly many components on this, I'm quite free to choose what my board outline is, although this is rather small. I figured we don't have to go for a 4-layer board for this design. This is a simple 2-layer design. On the top layer, I have all of my components, all of my traces and routing. And on the bottom side, I predominantly just have a ground fill, and we'll go more into detail how to segment up a 2-layer PCB in this video. But for this design, this was simple enough that I don't need internal planes. I don't plan on putting this into a product. For example, I don't plan on selling this. This is for my own purposes for example, this quadcopter base station. And despite having USB high speed on it, RF on it, and some digital ICs, for this particular case, there wasn't a need to go to 4 layers. Also, in terms of routing out, you see I only had to jump to the bottom layers a couple times. The first tip I'd like to give, however, for 2-layer designs is to make sure that if we're going with, for example, a cheaper 2-layer process, we also have to adjust our design rules to match that cheaper process. So typically, if you want to take advantage of these fairly inexpensive prices, again, regardless of what PCB manufacturer you go with, their default PCB service will be, for example, a minimum track spacing of 6mm, which is about 0.15mm, and a minimum hole size of 0.3mm. So if I change, for example, the hole size to be smaller, that might increase the PCB price. If I change to a different solder mask color, that might increase the PCB price. If I change the surface finish, that will change the PCB price, and so on. So there are certain things that will also influence the design constraints in our PCB design tool. Therefore, going to 2D view and looking at the smallest trace width I'm using, for example, in this design, going to the properties on the right-hand side, that's a 0.152mm trace, which is equal to a 6mm trace, which is suitable for these very basic PCB prototyping places. If I go to design rules, I set up my rules and constraints to match typical 2-layer PCB manufacturers' design constraints. If I were to go any lower in my design rules, for example, if I have a minimum trace spacing of 0.127mm, then that will probably increase the PCB cost, which is something I'm maybe trying to mitigate by going with a 2-layer PCB. Of course, this is entirely design dependent. Sometimes you will have to go with smaller PCB traces. Just be aware that if you're trying to cut cost, for example, if you're trying to go with a 2-layer PCB, then that might be a cost adder. Of course, the same thing can be said for 4-layer and higher layer count PCBs. As usual, it is just something to be aware of. And again, that's why I went, for example, with a 0.3mm holes generally over this board, and the smallest trace width being 0.152mm or 6mm, because this does not add any cost to this 2-layer PCB. As usual, you can find the design constraints by going to your preferred PCB manufacturer of choice. For example, for PCBWay, going to their capabilities section. If we scroll down on that page, we can find PCB capabilities for quick turn PCB, as well as for advanced PCB. And there might be in between steps. Make sure to speak to your manufacturer. But for example, for the quick turn PCB, we have to stay within certain constraints. Now keep in mind, even though they could do a 0.1mm trace, even with their quick turn capabilities, that doesn't mean that won't add cost. As we can see on the right hand side, it's strongly suggested to staying above 6mm, so 0.15mm to save cost. Same thing goes for spacing, drill size, and so on. For example, here, any drill sizes smaller than 0.3mm will be subject to extra charges. So make sure you're staying within the design constraints if your goal is cost, manufacturing ease, reliability, and so on. As we've already seen with this particular design, what I'd like to do with my 2-layer designs, if at all possible, is keep all components on the top layer, and this is what I try to do with multi-layer designs as well, is keep all components on a single layer. That just eases the assembly process. In particular for 2-layer designs, I want my components on one single side, if possible, and the majority of my routing, that includes signal and power, on one single side. Typically the primary side might often be the top layer. Then on the bottom side, I want a pretty much uninterrupted solid ground reference plane. This will be the system ground in the design. Typically, of course there's a few exceptions, but typically I want a solid ground fill on the bottom layer to serve as my reference. Signals and components on the opposite layer. This makes sure that we have somewhat of a reference right below the signals and components on the top on the bottom layer, and then we have somewhat defined return paths. Keep in mind also this view, we can see that the top layer and the bottom layer, that distance is typically very large for a 2-layer PCB, typically around 1.6mm in thickness. So actually the return plane, in this case the bottom layer, is quite far away from the top layer. So we'll have quite a lot of electromagnetic field spread, and typically we might have worse EMI performance. Compared to, for example, a 4-layer board where the reference layer, the ground plane, for example, if it's an internal ground plane, might only be a fraction of a millimeter away from the signal. So 0.1mm, for example. So other than having a solid reference plane on the bottom layer, if possible, you can also try to bring that reference plane closer. So again, looking at PCBWay, the nominal board thickness is 1.6 millimeters, but we could reduce the board thickness to bring the top and bottom layers closer together. So we could do it 1.2 millimeters down to 0.8 millimeters, and that actually doesn't increase the price usually if you go down to 0.8 millimeters. Keep in mind, halving the board thickness from 1.6 millimeters to 0.8 millimeters does make the board, especially for larger designs with larger surface area, quite a lot more flexible. So there are mechanical considerations to take into account when you reduce the PCB thickness, and that's true for any design. But if it is an option, you could maybe get improved signal integrity and EMI performance by bringing the bottom ground plane, if it's on the bottom, closer to your signal, to your forward paths. Going lower than 0.8 millimeters, for example to 0.4 millimeters, will probably increase the board cost, and keep in mind this is very, very thin. So 0.8 is probably the lowest I would go. That being said, for this RF stick PCB, I went with 1.6 millimeters because I valued the rigidity of the design, even though it's a very, very small and compact design, over bringing the planes closer, because again, this is completely private use. I'm not going to sell this. This won't have to undergo testing. But to summarize, keep in mind, try to keep components on one layer, on the same layer, try to do your signal and power routing if possible, and try to keep the opposite layer as unbroken as you can with a solid ground plane. As with pretty much any PCB design, component placement before you start routing, placing vias and so on is absolutely critical. We want to place our components first, and specifically for two-layer designs, this is very critical that we place our components in a sensible way with sensible rotations, sensible positions, that we make our routing life easier. Our routing life is constrained, as we'll see, usually typically to one layer, and the other layer is a solid fill, if possible, so we want to minimize the amount of rat's nest crossings. A good placement will minimize the jumps we have to do, and minimize the distance between components and their connections. So for example here, I've just made a copy of this RF PCB, took off all of the components, and I've just placed in these two centralized Cs. So the FTDI USB to SPI converter and the CC2500 RF transceiver. Now if I just keep them in their default positions and move them close together, okay, they might be close together, but is the routing optimal? That's why I like to color code my nets. For example, all these blue colors are the SPI lines that go between the RF transceiver and the USB converter, and for example, the red nets are my powers, and gray is ground. So if I have them like this, so for example, if I route out from one of these pads, I have to go all the way around, like so, into the top. Now that might be okay if I have just one single trace, but I have quite a lot of components, and please ignore the fact that there aren't any of these peripheral components such as decoupling capacitors around this, but if I have quite a lot of traces and components, I'll have to do this and it'll be very, very tight and I might have to jump. Also, this trace length is unnecessarily long. So what I could do, for example, if I just rotate my component by 90 degrees, I might have shorter connections between various pads and pins. Okay, I might still have to do jumps, but the jumps might be shorter and there might be less of them. We might have less rat's nest crossings. Also, if you're using microcontrollers, and in this particular board I am not, for this particular board I have pretty much fixed pin outs, for example for the SPI lines and these various other signal lines, but for microcontrollers, for example, just as a demonstration, I could move around my signal pins, of course within the constraints of that microcontroller. So in certain scenarios, I might be able to choose a pad and make sure and move that around that I have less rat's nest crossings. So for example, with a microcontroller design, I could move my pin out around that makes my routing or routing life far easier. For example, like so. Just as a very, very basic demonstration. Of course, that is in many cases not possible. So in that sense, we just have to rely on sensible placement and routing. In the case of the RF stick, this RF dongle, this was somewhat of a sensible placement. I have the FTDI chip very close to the CC2500 IC. Then of course I place all of my decoupling capacitors and critical components such as reference resistors, CMOS oscillators around the parts, and that allows me to minimize the connections and hopefully minimize the amount of jumps I have to do to the bottom layer. So for example, the crystal oscillator, I try to place the output pad 3 very close to the input pad 18 of the FTDI, that I just have a very, very simple, very short connection between these two components and pads. So again, with any PCB design, make sure you place your components sensibly before you start any routing. With sensibly placed components, for example decoupling capacitors close to the relevant power pins, I can keep my connections short, I can minimize the amount of crossings I have to do. For For generally any PCB design, what I try to do is of course do a proper layout and placement. First, before I start any routing, place my vias approximately. That might be for ground, for power, depending on how many layers I have. For a 2-layer board, of course, we will place predominantly just the ground vias, and if we can expect them, signal vias that we use to jump over other traces, for example. Once you've done your placement, for example, here I've gotten rid of all the traces and polygon pores and so on. This might be your starting point before you start routing. What I then want to do is route all of my critical traces first, as usual. So that might be, in this case, USB and the SPI lines, and then the less critical traces after that as well. You will have to probably iterate on the placement of the components. So even though you think the placement of this oscillator might be a good idea to start with, because of constraints of the 2-layer board, you might have to move things around to make sure you can maybe minimize connection lengths or minimize the number of jumps you have to do. So it is, of course, an iterative process. But critical traces first, after your layout and placement, and after you've placed your ground vias as a minimum as well. Again, and I can't repeat this often enough, a good layout and placement of your components makes your routing life so much easier and quicker. When it comes to power routing, again, for 2-layer boards, for most cases, you don't need a dedicated fill or plane. And again, if you do need that, you should probably move to higher layer count board. But what I like to do is keep my power traces as wide as I can where I have the space. So for example, here I have 0.6 millimeters, just as an example. And when I need to, I neck down. So for example, coming from these wide traces, I go into this, for example, decoupling capacitor, and then I neck down so that I can go into the pad of my relevant component, in this case, this IC. So I try to make my trace as wide as the IC pin and get wider as soon as I can. If I try to go to these hard to reach places, so for example, routing my wide trace into a different decoupling capacitor, I sometimes have to neck down. So I'll try to stay as wide as I can, and then I slowly neck down, keep that size until I can neck back up again to a larger size into the decoupling capacitor and into the relevant power pin. So that's how I like to do my power routing in general, also for multi-layer designs. For example, for this RF dongle PCB, on my top layer, I have all of my components and the majority of my signal and power routing. On the bottom layer, I then have my pretty much solid, somewhat uninterrupted ground plane, which acts as a reference to the top layer predominantly. As you can see, I've routed power, so these thicker traces are my power routing, and that's typically fine for most designs. If you're in an area where you won't get away with routed power, you probably should be on a 2-layered PCB design anyway, and that's a topic for a future video. Regardless of that, what we want to do is, as we've alluded to before, is try and keep the bottom layer as solid as we can and try to minimize the jumps and cuts that we do. Now, unfortunately, I did have to do a couple here, but typically that is okay, but we want to try and keep them as small as possible. We don't want to try and break the ground plane up because that'll, so to speak, and very simply speaking, disturb the return currents in that layer and disturb the reference. So for example, if I do have to do a jump, for example, this 3.3 volt trace have to go to these bypass and decoupling capacitors for the FTDI chip, I dig down to the bottom layer, try to do a very, very short jump. You can see the total trace length is just about 2 millimeters. Dig up again with a via as soon as I can, as soon as I'm clear, and then into the relevant components and traces. So this is for signal and power routing. Similarly, I try to keep those jumps very, very small. Conversely, I could have, of course, dug down right at the top at this trace, but that would mean it would have a far longer cut on my bottom layer, which should be predominantly an uninterrupted ground plane. So by going as close as I can on the top layer, then digging down and having a very, very short jump, I slice up my ground plane on the bottom layer far, far less. In certain cases, that might be unavoidable. There might be better ways of doing that, but the idea is keeping your ground jumps as short as you can. With that small jump we just saw from the previously 3.3 volt via under the USB differential pair to this 3.3 volt via, we saw that we actually had cut the reference plane under this USB high-speed path. Now for a design like this, which isn't going to be tested, even I tested, and given that this is on a 2-layer board anyway, usually this isn't too much of a problem having these short jumps, even if it's maybe under more critical traces. If you'd like to improve that, however, you might have to do a longer jump. For example, I've just rerouted this trace like so we still have essentially around the perimeter this 3.3 volt large power trace. So what we could do is from the bottom, route up to this new via, then we jump to the bottom layer, and have this far, far longer ground cut, and then jump up to the via we had previously that goes into these various decoupling capacitors into the FTDI IC. In this way, we are cutting the ground plane with a far longer trace, so we do have this large cut in the ground plane and ground polygon pore. However, this cut, if we see this view, is not underneath any critical traces. The cut we see here is simply under some ground and some power pads, so basically all DC, so that might be a fair compromise that we don't have to do the cut underneath, for example, this USB differential pair. So that might be a preferred scenario. Also, when you're doing ground jumps, I like to space my vias further apart. So if I, for example, place my vias close together, you can see the copper won't actually flow between these vias. Whereas if I place my vias further apart, you can see I can get these slivers of copper to flow between my traces and vias. So that's why I like to space my traces and vias further apart. So when I do have to do these cuts, at least I get some copper slivers flowing through. Again, looking at this kind of see-through view where we're looking at the top layer, but we see the bottom layer in the background, we can see, for example, these SPI lines don't have a well-defined reference path or plane underneath because we are cutting the reference plane underneath on the second bottom layer. So what you could do is again increase the length of these cuts, but move these cuts around. So for example, if I drag this a bit to the right, re-pour my polygons, we can see that now more of the traces on the top layer have more area that is actually ground underneath looking at the see-through view. So we could improve that even further. For example, something like so, I've now adjusted essentially the bottom traces that we still have slivers flowing through these vias and around these traces. But now if we just look at the forward paths, so for example, RF MOSI, we can see that this still has somewhat of a better defined return path underneath. Of course, there are still some cuts, but we could move these and play around with these even more. For example, that we don't have any cuts underneath these particular traces, even though that does mean in this very crude example that we might have to increase the length of our cuts. And then again, keep in mind that these distances between top and bottom layer are very large, so the amount of benefit you might gain in any case might be minimal. But it is a good thing to keep in mind, however. Then for the top layer, to perform any ground connections, all you have to do, because we have a pretty much solid reference plane on the bottom with ground, all we have to do is then on the top layer, do a trace or polygon pour for ground, and then simply dig ourselves down, place a via to get to the bottom layer and attach to this overall ground reference plane. That's then what I also like to do for two-layer boards. In most cases is flood the top layer also with a ground polygon pour, so I don't have to manually make those connections to the various ground pads and the vias on the top layer so that we can connect to the bottom ground plane. For two-layer boards, because the spacing between top and bottom layer is typically rather large, having a ground plane or polygon pour on the top layer just filled in can also improve the references because, for example, the clearance between my trace and the ground copper fill on the top layer will of course be closer than the distance between the top and the bottom layer, so you might get improved field coupling and maybe an improved reference for those by pouring ground on the top layer. If you do flood both layers with ground, make sure, as I've done here, to add in numerous stitching vias to tie both the top and the bottom layer fills together. As you can see, I've placed various stitching vias around the board. I'll leave this article by Zach Peterson in the description box below, but he'll tell you everything you need to know about stitching vias, how they should be placed, the spacing between them, and so on. So make sure to check out that article if you're interested. But definitely keep that in mind, that in general in PCB designs, if you have multiple ground layers, you typically should stitch them together at specific intervals, depending on the wavelengths present in your design. We also have this 2.4 GHz RF section on the right-hand side of this PCB, connected to this RF transceiver and this PCB chip antenna. Now, RF designs are very common on two-layer PCBs, and I'd like to show you what to pay attention to when you're implementing those. Again, this is a 2.4 GHz RF analog system, so calculating the wavelength of this signal on our PCB, we simply do V equals lambda f, so the speed of light is the wavelength times the frequency, but keep in mind we have different dielectric for our PCB. For an FR4 PCB, in this case the two-layer PCB, a typical dielectric constant might be 4.6, so therefore we take the speed of light, 3 times 10 to the 8 meters per second, divide that by the square root of our dielectric constant, and also divide that by 2.4 times 10 to the 9, so that's 2.4 gigahertz. And we get that our wavelength is 58 millimeters approximately. So this is the wavelength of the frequency of our RF section in the dielectric material of our PCB. Now, we can define terms such as critical length in a PCB, and that's typically a 10th or 20th of the wavelength we find out here. So if we divide that by 10, and again, this is in millimeters, we have a critical length of about 6 millimeters. So anything below that critical length, anything below 6 millimeters for this particular design, for this particular frequency of interest, anything below 6 millimeters, anything below this very approximate critical length can be considered, so to speak, invisible to the waves we're dealing with. So as long as we can keep our trace lengths far shorter than our wavelength, far shorter than the critical length, we really don't have to worry about impedances of our traces. So therefore, I try to place my components as close together as is reasonable for manufacturing and assembly purposes, but also I try to keep these RF trace sections, so for example from out of the pad of the RF transceiver into the pad of this first capacitor, that trace length is very, very short to stay far under that critical length, so I don't really have to worry about sizing this trace correctly and calculating RF parameters and so on. So in 2D view, if I just do a random measurement, let's see what 6 millimeters looks like. So I've just measured about 6.5 millimeters here, but you can see 6 millimeters is actually comparatively quite large to any of these trace sections and any of these small 0402 components. And that's exactly why I did it this way. So for example, looking at a typical trace section here, that's maybe around 1 millimeter in length, so far below the wavelength of the frequency of interest and far below the critical length. Therefore, I can size these traces pretty much however I want for this very simple RF system. And again, the reason why I place the components very close together, so I don't have to create longer than necessary traces. If you do need impedance matching, if you have long features in comparison to the wavelengths of your frequency of interest, then of course you have to worry about impedance matching, various material properties, losses, and so on. But for these very simple systems, it often suffices just to keep the traces very, very short and the components small relative to the wavelength of interest. Again, many RF PCBs are done on 2 layers, but there are certain things to take into account when you're trying to control the impedance of those traces. So I'm just going to use Altium's built-in 2D field solver. So I've got to the stack up tool. I've got my PCB stack up, which is 2 layers, top layer, dielectric, bottom layer. We're assuming our bottom layer is our reference. So if I go to the impedance tab, if I add a new impedance and that defaults to 50 ohms, if I just select the top layer, we want that to be 50 ohms, you can see the trace width is automatically calculated to be at 2.8 millimeters. So very, very, very large. And this is because we have such a large and thick dielectric between our top signal layer and our bottom reference layer. That means we have about 1.6 millimeters in between those, which causes this large increase in the trace width for a target impedance of 50 ohms. Compare that to, for example, the typical FR4 4-layer PCB, that trace width might be at 0.3 millimeters or less. So about 10 times larger we need for a 2-layer PCB. Now, if I try to draw a 3mm PCB trace, this is about as wide as a 3mm PCB trace is, and this would give approximately a 50 ohm impedance, compared to the trace width I did here, which is a 0.25mm trace. So it's pretty much impossible to fit that 3mm trace onto those pads, so therefore I try to keep my distances and my traces as short as I reasonably can. Now, there is of course another way of getting around this very large trace width, so I could actually do a coplanar waveguide with a ground layer. And for example, looking at this random image, we have our dielectric of thickness H for our 2-layer PCB, about 1.6 millimeters. We have a reference, ground reference on the bottom, our signal layer at the top, and we have some spacing to some ground fill left and right of that trace. And this is a coplanar waveguide with the ground. So you can use, of course, free calculators as well on the internet or ask your manufacturer, but I'm just going to use the Altium tool. I've selected single coplanar. And so for the same target impedance of 50 ohms on the right-hand side, I can look at my transmission line, I can play with the clearances and so on. So for example, if I have a clearance to my conductor at the top of about 1.152 millimeters or 6 mil, and the distance to the reference plane below of about 1.55, 1.6 millimeters, we can see that for this coplanar waveguide with ground structure, I only need a trace width now of 0.7 millimeters, but that's assuming that I have ground poured at a clearance of 0.152 millimeters around the trace, again, as we saw in this image. So having ground fill on the top can reduce the trace width you need to hit a certain impedance, for example. But again, even 0.7 millimeters is still quite a chunky trace. So that's the trace I've drawn here. And that requires that you have ground filled left and right of the trace with a clearance of 0.152 millimeters. So again, I'd strongly suggest, unless you're dealing with very, very critical RF systems and you're dealing with something such as these very simple RF transceivers, just keep your traces and components reasonably small below an approximation of the critical length, and you will be, in most cases, fine. A final point I'd like to make, rather than a tip for 2-layer PCBs, is just the comparison between a 2-layer and a 4-layer PCB. This picture shows the comparative dimensions and layers in a 2-layer versus a 4-layer PCB. On the left-hand side, what we saw, very simply speaking, we have copper layers top and bottom with a dielectric material in the middle. And normally the PCB total thickness will be 1.6 millimeters. Keep in mind these diagrams aren't showing the solder mask, silkscreen layers, and surface finish layers. As an approximation, a 2-layer PCB is shown on the left. On the right-hand side, a 4-layer PCB, where we have signal, then we have a very thin dielectric material called a prepreg, then we have typically an internal layer, and we might assign that to be ground or power. Then we have another thick core, but keep in mind this is still going to be thinner than the core on a 2-layer PCB with equivalent final thickness. Then we have another internal layer, could be another ground plane. Then we have another thin dielectric, and then we have our bottom layer. What's important to note is the dimensions of the dielectrics and the overall spacing between, for example, a signal layer and an adjacent plane layer. On the left-hand side, if we have the top as a signal layer and the bottom as a ground layer, we have this very large separation due to this very thick core of 1.6 millimeters. Whereas on the right-hand side, between a signal and a ground layer, for example, if we've constructed our stack up like so, we might only have 0.1, 0.2-ish millimeters between our forward path, our signal layer, and our return path, our ground layer or power layer, for example. This overall means we get better field coupling, closer return paths between signal and ground. For the same spacing of traces, we might then get less crosstalk for a well-constructed 4-layer PCB. We might get less emissions, better signal integrity performance, and so on. So there are trade-offs between 2- and 4-layer PCBs other than the cost. Keep in mind, we saw the cost difference even in volume might only be a couple of cents. Now, of course, this depends on the product you're designing for, but you also have to take into account the design time it takes to make everything fit on a 2-layer PCB versus a 4-layer PCB. It might be quicker, you might have less hours you have to spend yourself or for a design engineer to work on a 4-layer PCB compared to a 2-layer. So you might be saving cost in that sense as well, and also you might be getting better EMI, SI performance and so on just by going to a 4-layer PCB. And that's something you should always keep in mind. I'd also strongly suggest checking out this 2-layer versus 4-layer EMC test PCB done by Dave Jones of EAV blog, and I'll leave a link to that in the description box below in case you're interested. I hope these quick tips gave you an overview of what to pay attention to when you're designing for 2-layer PCBs. That is, try and keep a solid reference plane on an adjacent layer to the signal and component layer. Try to stay within the manufactured constraints for quick-turn PCBs. Try to keep critical signal traces as short as you can, and that means you should also have done a fairly sensible job with layout and routing, making sure you rotate and place components sensibly. That allows the minimum number of jumps and cuts in your ground layer, and allows for short connectivity. For RF sections, we want to keep our traces short if possible, because we don't want to have to deal with these very wide traces that come with using such a thick dielectric material. Of course, we've only scratched the surface, but these are general guidelines that I find useful for any 2-layer PCB design I do. So thank you very much for watching this video. Again, I hope it was helpful, and I hope it helps you out with your future 2-layer PCB designs. If you haven't already, please make sure to subscribe to stay up to date with any latest embedded systems, hardware design, PCB design videos, and more. Thanks again for watching, and I hope to see you in the next video. Bye-bye.